take it off of test mode, and then you're ready to hit your counts. Okay? But before you do that, you need to make sure that you have your machine peaked. So we typically take a cesium source and put it into the well counter. You notice that over here we have voltages. It starts at 200 down here. Can you guys see that, by the way? Okay, so it starts at 200, 400, 600. Okay, so you have increments of 200 volts here. And then this is what they call a fine adjustment. So right now, if I had this thing set at 800, okay, this would be 820, 840, 860. So I can increase what they call fine tuning on your radio sets. You used to have a button that you would push that would get you close to the station you wanted to listen to, and then you'd have a knob that you would use to fine tune it to get right to where you got the best sound. And that's what we're trying to do with this. Okay, so for your uptake probe and also for your well counter, what you do is that. Over here, this determines how long you count it for. Excuse me. But what you're trying to do is this, okay? This is on page 119. Okay. This is the number of counts that you get. And then you plot the number of counts versus the voltage down here. Okay, so this is the voltage that I'm using to collect those counts. Okay. It's supposed to be where 1 volt there equals 1 volt on your for the radionuclide, but it doesn't really work like that. Okay, so you notice that at about 660 volts we get the maximum peak. We get 12,000 counts roughly. Okay. The reason we want that is because every day when I do this test, I should have about the same voltage setting. You know, it should be somewhere between, maybe 655 and 665 or something. So that tells me that the electronics aren't drifting. You know, in other words, the voltage that I use should be the same voltage on a day-to-day basis. It shouldn't be going all over the place when I do this test. If I use the same source of radiation, right? You with me on that? Fresno, you guys okay up there?
Yeah.
Do you guys do this every day? You do your check your well counter?
I have done it.
Huh?
I have done it.
Okay. Have you done it, Mr. Singh?
You go to QC?
Yeah, you can see every morning.
Oh, not this quarter. Yeah, me either this quarter, but last quarter I did.
I haven't done it QC.
I can't emphasize, I know a lot of this stuff really sounds redundant and stupid, but as I told you in those letters that they've already hit 4 facilities this month where my former students work at, unannounced. And this is one of the things we're going to look at. Are you doing the quality control on your well counter and uptake probes? And right here we're looking to make sure that the voltage is okay. The other thing that we do is what we call the full width at half max. Okay? So in other words, what we're trying to do here is measure the energy resolution. Typically for an uptake probe or a well counter, it should be 10% or less. And the way that we calculate it is with what we call the full width at half max. What did I do with my pen? Oh, it's in my pocket. What did I do with my head? Okay, so what we do with this, we find the peak, which is 12,000. Half of that is 6,000. So you come down here and you draw a line, okay? And where it intersects the plot here, you go down. So it looks like it's about 625. Is that about right? 625? Okay. Then we go over here to where it intersects over here, it's about 700. So basically, my full width at half max is 75 kV. Now to calculate the percent resolution, the difference divided by the energy of the radionuclide, so this is going to be 662, or whatever the photo peak is. I'm going to just say it's 662. Yeah, or 660. And then times 100. Okay. So in this particular case here, it's about 10.9%. Okay. They were a little bit, they calculated it as being 72 kV. But the two things that you want to watch for on this is that percent resolution, because right now you're exceeding the allowable resolution. Trying to see what they say. They're saying that it should be 8 to 12% in here, but the people that I talk to tell me it should be more than 10%. But you know, but the things that you're looking for are, okay, what was the voltage that you used, the voltage setting? That shouldn't change on a day-to-day basis. And then the energy resolution. Now in the textbook they're saying 8 to 12%, so that would probably be what you'd have on your board exam. Okay? But that's one test that we do. Okay? Some other things that we have here. What you will notice is the sharper your peak and the narrower the distance between the width, the better your camera is going to perform. It has better resolution. Okay? So when it gets wider, that's bad. And remember, I also told you that we do this to measure the bolus injection. Remember that? When you guys do a flow study and you're looking at the kidneys or you're looking at the heart, we do the same thing. Now let's say that you're looking at the kidneys. When you're analyzing the flow study, you see the activity come in, it goes into the right atrium, right ventricle, out to the lungs, back to the heart, down the aorta, and then to the kidneys. And typically you put a region of interest over the aorta, correct? Have you guys done all, have you all processed it? Okay, why do you put it over the aorta? To do what?
Take out the aortic counts or something?
No.
Compare them?
No. Well, you're doing a couple of things with it. Remember, you also have a background out here, too, that you subtract. Sometimes you just have one region of interest as the left kidney, then the other region of interest is the right kidney, and then you have aorta, and you have background. Some places do the bladder, some places do the cortex, some places do the cortex and the medulla. Anyway, so the thing that you're looking at is this. Okay, if you look at your aorta curve, you're going to get the blood arriving, and then something like this. And then down here you have the time. So let's say that each one of these represents half of a second. So here's 0.5, here's 1, 1.5, 2, 2.5. Okay, so again, you look at the peak. Let's say there's 1,000 counts here. So you go down to 500 counts. And you find the corresponding time for that. Okay, so basically we have like 1.8 counts, or 1.8 seconds here, because this is my time, minus 1 second. So my bolus is actually a duration of 0.8 seconds. If it's over 3 seconds, then that means your bolus is not good. You took too long. Okay? A bolus should be a very tight, small concentration, high activity, arriving in a short period of time, less than 3 seconds. Okay? This is how you calculate it. We do it for heart studies, we do it for any type of flow studies. The other thing is if somebody had, let's say, 20 millicuries, but it was in 3 ml, okay, it takes a long time to inject 3 ml, so what would happen is you'd see a wider in here. Okay? Or if they start and stop, what they call stuttering. They start injecting it, they're not sure if it got in, so they stop and then they re-inject some more. So they start and stop. You can analyze a bolus and see whether or not it's something you can use.
Did you say the sharper the peak, the better the resolution?
Yes. Yeah, let's see, on these calculations that they have here, this one here is probably junk. If you measure this one here, this is like 10,000. If you go down to 5,000, you've got 620 and maybe 7 something. Looks like it's pretty close to 710. So 710 minus 620 is what, 90? So 90 divided by 662 is how much? 11%? Yeah, that's still not bad. But that's what you're doing this for. You want to make sure that the voltage is the same. And then this is the chi-square that we learned about before, because what you're going to do is take your cesium source and count it 10 times or however many times you've got time for, and calculate the chi-square to make sure that it's okay. This is the section we're going to be working on now. Well counter efficiency. Why would that be important to you guys? It says regulations require wipe tests be recorded in BPM. So in order to convert counts per second, you must know the efficiency. Huh, how would that play in here? If I have a source of radiation that I know is 1 microcurie, and I put it in my scintillation detector, and I count it for 60 seconds, what should I get? Huh?
Certain number of counts.
Certain number of counts. Okay? Y'all agree with that? If I put a source in there and I count it, I should get a certain number of counts. How many counts would you expect to see if my detector is getting 100%? Can you guys calculate that? Huh? How many counts are there in a microcurie?
So it's something to get back on the simulations. A microcurie? A microcurie is 37 megabecquerels.
So it's 37,000 counts per second, right? If I put this in here and I count it for 1 second, I should have 37,000 over here. If this detects 100% of the radiation. Do I always detect 100% of the radiation? Yeah. If I count it for 60 seconds, then I would multiply that times 60 seconds. Okay, but I'm just going to pretend that we're counting it for 1 second. We'll keep it easy for me because my brain isn't too good right now. Okay, so that's what I would expect with 100% efficiency. Okay, all the radiation that's produced is all the radiation that's seen by the equipment. Well, let's say that I see 18,500. Okay. So, what happened? Okay, it's 50% efficient. So why am I missing the counts? Where are they all going? Huh? Okay, there's dead time because the electronics on your equipment can't keep up with all the radiation. Remember that the crystal, this is a crystal from an uptake probe. Basically, these things are shielded in aluminum. Okay, notice it has aluminum on 3 sides. Aluminum has a very low atomic number, so the photons go through there without being attenuated, or most of them do. The ones, not all of them make it through, they get absorbed. Okay. This is the crystal, it should be white. Well, actually, crystals are not white. Does anyone know what color the crystal is?
Clear.
It's clear. Yeah. So you're not seeing the crystal. What you're seeing is what we call the reflecting powder. Because what they do, okay, you have aluminum here surrounding it. And then they put this white powder called reflecting powder. Now the reflecting powder, we'll talk about it a little bit later. It can be anything from aluminum oxide, like we use for our Luxel badges, or it can be titanium dioxide or magnesium oxide. Okay, all of these materials are very white. So if I surround, or if I put this layer on here, and then I put a crystal on top of that, so this is my sodium iodide crystal, put 2 dots activated with thallium. So when the radiation comes in, remember that light is produced and goes 360 degrees. Okay, I don't want to lose that light. So I put reflecting powder here, so any light that's reflected towards the outside of the gamma camera is now going to go up and be observed by our photomultiplier tube. Okay, does that make sense? So what you're seeing in here, this is the white reflecting powder. Now, why does it look yellow? And why is this crystal all cracked?
This is old.
Huh? Well, it's old. The reason why it's yellow is because somehow water got in there, moisture. You remember somebody, I think Ashley, you were the one that sent the answer to that question about the measles.
Me.
And Cynthia. Okay? Anytime you get moisture on the inside of a gamma camera, you're going to start causing the sodium iodide to break down. That yellow is the iodine. It's the separation of the sodium and iodine. So, but this thing cracked. It actually shattered. And the reason it shattered, it was because it was in my trunk. And there was a sudden change in temperature. Okay? These crystals, you cannot leave them unexposed, uncovered. In other words, you don't take the collimator off and leave these things unprotected at night. You never leave a collimator off of a gamma camera. The temperature change The collimator protects it from that. Physical dropping of stuff, you know, people, we have these repair guys come in and replace light bulbs. One of my collimators got damaged. Of course, they didn't tell us. They dropped one of the lights, the fluorescent lights. Next morning, we had a cold spot where the septa had been damaged. So that's why it's a good idea. I always believe in doing what they call extrinsic floods. That's what the collimator on. Because that way, if there's been any damage to your collimator over the night, you're going to pick it up. Okay? And then the other thing that they do on this, they have what they call optical gel. I was telling Greg here, optical gel comes in a container about the size of a hand cream. Costs about between $3,000 and $10,000. It is optically pure. They can only use it one time. So as soon as they open up that jar and they use it to grease your PM tubes, it's done. They have to throw it out. So about $3,000 to $10,000. Yeah, it's. I mean, it doesn't happen very often, but you know, it happens. So you just make, and we can grow these crystals almost any size we want. You can't see how thick this is, but typically for most gamma cameras, it's anywhere from about 1/4 of an inch for what we call high resolution crystals, all the way up to about 1/2 of an inch for high sensitivity crystals. In other words, the thicker it is, the more radiation it's going to stop. Okay? But the problem is you lose resolution. One of the questions that they always ask you is, what is the relationship to resolution and sensitivity? And as Greg said, it's an inverse relationship. If I double the sensitivity, my resolution is cut in half. To give you an idea of how that works, does anybody know what the resolution is of the human eye? And what do we measure resolution in? I never thought you'd have
As
to learn
far
that.
as how far you can see, or
Yeah. I can see the moon at night, so
There's
I've got
like-
good resolution to 240,
like you could see
300,000
a
miles.
candlelight so far away, some kind of fact like that.
How fast the eye picks up images.
Well, it's a little bit, okay, what it actually is, you guys do this every week. It's called, you guys do a bar phantom check, right? I've got a bar phantom in my car that I'll bring back at lunchtime. But basically, you've got different size bars. You have usually like a 4-quadrant phantom, and you've got some that are thinner, right? Okay. What you're measuring is what we call line pairs. Well, you have one lead strip and then there's a piece of plastic, that's one line pair. So when you take a picture, you're actually looking to see how many line pairs your gamma camera is able to see. Okay, you guys have done bar phantoms, right? Okay. So the thing is, okay, human eyes can see about 10 line pairs per millimeter. If you guys have supervision, you can probably see 20 line pairs per millimeter. Okay? So that might be with a standard image looking at a monitor. One of the things that you guys are also supposed to check, and I don't think anybody ever does, is the computer monitors. You know, you guys do your floods every day, but do you actually look and measure your monitor as well as the images that it produces? Huh? I see a lot of smiles out there, that means no. Okay? So your image is only as good as the monitor and its adjustments. Monitors go out and have problems. You have people that come in there and want to play video games, and when you're not there, and come in and you wonder why the heck your monitor looks so weird? Okay. Well, the thing is, like I said, if you increase the sensitivity, let's say you go from one that detects, 1,000 photons per second to 2,000 photons per second, so I've doubled the sensitivity. Because of that, my resolution will be cut in half. Does anyone know how we measure the resolution of the monitors, by the way?
Bits.
Huh? So we've been in a hospital now for almost a year, and
Isn't it pixels, like 800 by 600?
well, that's what you're putting in. That's what you think you're getting, right? Because that's what the computer tells you you're getting. So none of you guys have checked the resolution of your monitors, huh?
Is that where they got like the checkered pattern?
What's that? Have you checked the resolution of your printer's one? I thought that was actually the same thing. I'm sorry. You ever seen one of these? Okay, let me see if I can widen this thing out as wide as it'll go. In order to check your printer, now most of you don't print images anymore, right? Okay, but if you did, you would print this out. But since you don't print out your images anymore, you put this up on your screen and you look at it. So over here we have a line phantom. Okay, so basically the resolution of this thing is such you can't see the small ones over here. Let's see if I put it in the center.
They're really strict about doing this in the bottom.
Oh yeah. I don't know if this thing is not working as well as I thought it would.
Turn off the light.
Well, you can see that they have lines over here, but I think it's too bright. You can't see the small lines. This is what you're trying to determine. Can you guys see it over here? Are my fingers there? Let me see if I put something. There you go. Okay, in each corner there's one of these bar phantoms. Okay. And there's also one in the center. And then they also have what they call a contrast phantom here. And then they have all the different colors. They have about 16 different colors there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The eyes can only see about 16 shades of gray between black and white. Takes about a 30% difference in density for you to see something. Okay? But this is a phantom that's used for checking the monitor and also for checking your printer. Does anybody know what this thing is called? It's on your board exams. Here it is right here. SMPTE. Pattern. Test pattern. Okay? Whoever knows what that stands for gets an A for the day. Ashley? Mr. Singh?
I could look it up, but no, I've never done this.
Okay. And probably most people haven't. And probably most people don't even think about it. Because they don't realize that they're supposed to do this. Okay? This stands for the Society of Motion Picture and Television Engineers. Yeah. If you guys ever stay up late enough, when they shut down the TV station that you're watching, they broadcast one of these signals so they can test the resolution. Back in my day, they used to have, they'd put a picture of, they'd play the national anthem, and then they would put this test pattern up, and then the thing would shut down. Okay? But basically, you have to check the resolution all over the screen and all that kind of stuff. And that's on your board exam, guys. Society of Motion Picture and Television Engineers. And one of the other things that, did you guys ever hear about what we call the Moore effect?
MOV patterns.
Huh?
MOV patterns. M-O-I-R-E.
M-O-I-R-E, yeah. What is a Moore pattern? You guys see that? Okay. See how it gets these waves down here? Okay, that's a Moore pattern. What happens is when you're scanning in the same directions as these lines are aligned, you get kind of a wavy effect. But what happens to us in nuclear medicine, I want you to think, okay, let's just say that these are the holes in your collimator, and then you put a lead strip on it. How about that? That's Moore effect. What happens sometimes is when you align your lead, your four-quadrant phantom, if it aligns on the holes like this, you're going to get a Moore effect, and you're going to get these wavy pictures in it. Isn't that neat? You know, somebody gave me that. I mean, I was, you know, I don't remember why I kept this. Well, you can see it here. Oops. You can see there's kind of a Moore effect down here. The lines are not straight. This is what you're checking for with linearity. Okay? So trying to see if I can get it to do it. You can see that sometimes I can do it for a temporary thing here. What's happening is that if it's scanning at the same frequency as the lines here, then it creates that problem. But I was sitting there, somebody gave me these two things and said, I don't know what to do with them. I don't even remember what they were for, but anyway. Found a use for them. Okay. So let's talk about the gamma camera then. Once in a while we actually do talk about something that covers nuclear medicine. But no, on your board exams, guys, they will be giving you questions about that. So that's why I want you to be prepared. I want you to be like a Boy Scout, you know. The other thing I wanted to show you was, did you ever hear of a term called modulation transfer function? Did you ever hear that term before? Or did you ever hear of a term called Fourier transform? One of the handouts I gave you deals with computers. And basically, I was kind of sitting around, at my hospital not doing anything, and I started playing around. So I didn't realize at the time that I was going to create something that I could probably use. But I had a small 1mm piece of lead. I put it on my flood, and I took a picture of it. And then, just out for the heck of it, I put a profile slice through it. You know what profile slices are? Have you guys done those? When you create a region of interest, you're actually creating a profile slice. But basically, it just tells you the counts that are going in this direction. You can do these things diagonally, horizontally, vertically, any way you want. But what I wanted to show you is, this is how your imaging system works. You basically have a three-dimensional object but you have to convert it into a electrical frequency to send it to the computer. Does that make sense? When you're shooting an X-ray of a person, well, let's make it a little bit more personal here. Anybody recognize this study?
Mugger.
Mugger study, yeah, absolutely right. So here we have the right ventricle, left ventricle, here's the septum. What I did, like I said, I was just playing around. I put a liver marker down here. There's actually, 1 centimeter holes. There's 5 of them across there. And I just did a profile slice. So what you're seeing here is the full width half max for a 1 centimeter size hole. And this is just all background over here. So I went over here and I said, well, I'm going to put it through the heart. So there's 64 lines across here because I acquired this as a 64 by 64 matrix. So there's 64 horizontal lines, 64 vertical lines, and this is what the modulation, well actually this is called Fourier transform. Fourier transform is a mathematical process. It was originally designed for astronomy, but this guy, Jean-Baptiste Fourier, back in the 1700s, he's the guy that came up with this. He was using it for calculating planetary movement. And I guess it didn't work, so he says, shocking hoodoo. Well, went out and got drunk and never did anything again. But this is what created the basis for all medical imaging. You have to think for X-ray, nuclear, MRI, CT, we have to convert the patient's three-dimensional information into a series of frequencies that go to our computer. So what you're seeing here, okay, so here's the right ventricle, here's the septum, here's the left ventricle, and then all this is just background. Makes sense? The other thing I wanted to show you is this. Okay, how statistics play a game with us here. This is the Fourier transform of a low count image. Okay, can you guys see the object in there? I mean, you can see it here. But do you see it here?
One.
The end.
At the end? Well, actually,
No, that right in the
There's the
middle.
one that drops it.
well, see, when I don't have enough information, I'm losing its loss. It's actually still in the center. You're actually starting here. This up here corresponds to over here. I go down, so as you're going through the object should be right around here somewhere, but this is lost in what we call noise.
What's 0 out of 46? What is that?
Oh, that's the number of counts. I should turn it over here like that. Is that? Yeah. So basically, my object is lost in the noise. This is what we call signal-to-noise ratio. So this is not a very good signal-to-noise ratio. Compare it to this when I get more counts. Can you see it a little bit better? Can you see the change in the Fourier transform? Some places will just put a radioactive source here and take a picture of it, and then they'll draw a profile slice, and they'll calculate what they call the full width at half max for that. That's another application. If I turn this thing around like this, so I measure the peak up here, I go halfway down and I measure the width. Let's say that this measures 0.5 centimeters and this object measures 1 centimeter. That means that I've got a 50% resolution for that size of an object. This is how they can calculate resolution. Okay? That tells you the likelihood of you seeing a lesion or pathology or something at that size. Okay? But I just wanted you to see, okay, now over here again, here we have a noisy image, but you can kind of see that the object is there. And as we get more statistics on it, the image or the object starts sticking out better from the surrounding stuff. So, I didn't know I was ever going to be able to use that, but did it make sense to you guys? A little bit? You're going to hear that term MTF and modulation transfer function quite a bit, but Okay, so what we're going to start out with first is, since the collimator is the first thing that the radiation interacts with, by the way, want to see more? When you guys have two images that you put together like this, because there's 64 lines in there, see how we can create a moire effect with that? Huh? Yeah. Well, what it's saying is, though, that even, the scanning rate of your computer on this can create a moire effect you need to be aware of. Usually if it happens when you do the collimator, if you have a collimator and your bar phantom, all you have to do is just remove your collimator a little bit, remove your source a little bit, and that'll take care of the problem. Just change the alignment of the lead strips with the holes in the collimator, and you won't have that problem.
Isn't that kind of how a lithograph works? The thing where there's a picture, you look at it, and there's a lines, and then you turn it, the picture changes?
Yeah, sort of like that, yeah. Okay, on this one here, guys, okay, I'm going to change this a little bit because they kind of changed the definitions here. But you notice on this collimator here, okay, this is what we call a parallel hole, in that the openings on the septa are straight, okay? And so basically the definition of a collimator, a lot of you are going to be tempted to say it controls the energy of the radiation interacting with the crystal. Greg is shaking his head no. Mr. Viat, what do you think a collimator does? You guys change them all the time. You go from low energy to medium energy to pinhole. So what is that? What are you doing? Why are you doing that?
Because of the energy level. Since you usually use high energy for high voltage, probably not the energy level. It's has a higher energy and a higher voltage.
Okay. Okay. So you're saying then that the collimator is what determines what energy of radiation reaches your crystal? Is that what you're saying? Ms. Monica, what are you saying?
Photons traveling in a certain direction, the angle of it.
Okay, that's exactly what it does. Okay, the reason, let me just, okay, I want you to do a little experiment with me. Okay, the collimator only allows photons traveling in a certain direction to reach the crystal. That's the only purpose of it. We have what we call low energy all-purpose. We have high resolution. We have high sensitivity. In my day, we had about 6 collimators. Okay, we had a low energy, high sensitivity. We had a low energy, high resolution. We had a low energy all-purpose. So we had 3 low energy collimators. For medium energy, we had high resolution and high sensitivity. Then we had very, very high. We had low, medium, and high collimators. So we had about 7 or 8 collimators sitting out in the hallway. And you see, nowadays, because we've gotten rid of those high energy photons, we don't need the real, true high energy collimators anymore. Basically, you're just using low and medium energy. But what you're trying to do with that is, as you said, basically the thickness of the septa, the walls, how thick they are, determine its classification. So if we in most of the textbooks now, they say low energy is 0 to 200 keV, so you can change that on the handout. Medium is 200 to 400 keV, and then high energy is 400 keV and above. Okay. But since we don't have any, since we don't image cesium, that's about the only one that we have that's high energy right? Or 58 cobalt. So, the way that the holes are drilled is important because most of the time you're using a parallel hole. Basically, that keeps the image the same size. It doesn't create any magnification or minification distortion. Does that make sense? So when you're using a large field of view camera with a parallel hole collimator, basically the size of the organ that you're looking at is the actual size in the patient. Okay. When we're talking about diverging and I don't think anybody has portable cameras anymore, do they?
Yeah.
Do you have a portable camera?
And mission rate.
Okay, so with a parallel collimator, the organs are going to be the same size, basically. Okay, when they're talking about diverging, okay, they're talking about the septa are angled in. So if you have a large patient, then that's going to minify it. Mainly you'll see these on portable cameras because they only have like a 9-inch thing that, you know, if you were doing a lung scan, you would have to take, well, if you're using a parallel hole collimator with a 9-inch diameter camera, you would have to do the right upper lung, the right mid lung, right lower lung, and you'd have to do the left upper, mid, and lower. You'd have to do like a ton of pictures. But if you put on a diverging, so diverging means that here's, this is the image up here. So this is your crystal, and then here's your patient. So diverging means that it's going outward in relation to the crystal, so it minifies things. Now some of you may have a converging collimator. Okay, on a converging, okay, the septa kind of point in, so this magnifies the image. Most of, if you have one of these, you'd probably use it when you're doing like a neck for a parathyroid or something like that. Some people use the computer to electronically magnify it, but if you have a converging collimator, then you can actually magnify it with that. Okay. The other thing that I talk about, low energy all-purpose. Okay. Basically, to understand what we mean by all-purpose, versus high sensitivity versus high resolution. Okay, if we wanted something to have high resolution, typically we make it a very long tube with a very narrow opening in it. Okay, so this would be the opening here. If you want to see what it's like at home to do this,
A long tube with a narrow opening?
yeah, if you kind of think of looking around the room right now, you're getting in all of the, basically, information from everywhere, right? Okay, if you put your hand up like this and close your eye, this is what the septa and the collimator do. And then if you put your other hand up there, you notice that it's only allowing a little bit of light coming in a certain direction to reach your eye. And then you can make that even smaller if you want and get more pinpoint. And that's basically all you're doing with these collimators. A high resolution has a very long tube or a very long septa with a very narrow opening. Okay?
that is rarely focused, right?
Yeah.
Observation.
That's a symbol.
No, that's not a pinhole.